Let's suppose that I wanted to draw these marbles from a bag and I wanted to get two black. What is the probability that I get two black if I do this? So let me put these in the bag. All right, now assuming that it's completely random, what's the probability that I get one black? Okay, so there are three blacks. So there's the one black. Okay, now what's the probability that the second one I draw is a black? Well, if I don't put it back, then the probability has changed, and that would be a dependent event. So if I don't replace that, I'm now going to draw from a limited set. Okay, so then that probability is called the probability of a dependent event, where the drawing of the one affects the probability of the next. So let's look at what conditional probabilities are and how we would calculate them. So in this case, I have a different event A and a different event B, and they overlap here. Now, if I want to find the probability that event A occurs, I can just look at this. It's like 1, 2, 3, 4, 5, 6, 7, 8 out of the total number in here. So that would be 9, 10, 11, 12, 13, 14, 15, 16, 17. So it would be 8 out of 17 would be the probability that event A occurs. But I don't want to know that. I want to find out the probability that event B occurs given that A occurred. So knowing that A occurred limits my sample space to these values. So knowledge that I got what I got on the first draw affects the probability of me getting what I want on the second draw. So now I know that event A occurred. Now what's the probability that B occurs? When we look at this, we're going to be looking at now just the reduced sample space of A, and it's going to be this much here, the overlap. So this is our essential question. What's the probability that event B occurs given that event A occurred? Our notation is probability of B given A. That vertical bar means given that. So that's how we read this part. This just means given. Now I'm going to calculate that probability here. It would be 3 out of the total number in A. So that would be 1, 2, 3, wait, 1, 2, 3, 4, 5, 6, 7, 8. So 3 out of 8, that would be this probability. And generally, these conditional probabilities are easy to find. You just have to limit your sample space and do that. With the bag experiment, I pull out a black marble, and then I calculate the probability of getting the next black one with my reduced sample space. So that's basically essentially it. However, this becomes really important for us in general. So I'm going to write down how to calculate this. Here's basically how we calculate. The probability that event B occurs given that event A occurred would equal the number that are in here. So I'm going to say the number in this event, and this is known as A intersection B. So we have the number in this event divided by the number in the event A, which is our sample space now. It's the denominator. How many are we choosing from? So that's the number in event A. So we're going to have to calculate the probability of this. Now, generally, we can use this formula for calculating the probability because we can count the number. But sometimes we can't count the number. So I'm just going to say that it wouldn't make a difference if I used the probability of the event here. So let's look at just the probability of this. Well, I'll just write this out here. So we had a total of 3 divided by 8. Now, I'm going to say that equals the probability that we get the intersection. That would be the 3 out of the total number of outcomes, which is 17. 3 over 17 is the probability that this event occurred. The probability that A occurred would be 8 divided by 17. Now, as you can see, the 3/8 doesn't matter that we divided both by the sample space number. So this is generally the probability that A intersect B occurs divided by the probability that A occurs. Now, this is actually more important of a formula than this one. So we're going to be using this one, but these are just basically the same idea. So this is called the definition of conditional probability. That would be the probability that B given A equals the probability of the event A intersect B divided by the probability of event A. Now, actually, the reason that this is so important is it gives us a way to find the probability of the intersection, because I can solve for this by multiplying both sides by the probability of A. This is called the multiplication rule. And that means that I have the probability of the intersection of A and B equals the probability that A occurs times the probability that B occurs given that A occurred. I summarized these formulas for us on this sheet right here. Okay, so this is the addition rule and the multiplication rule, which we've looked at. So the addition rule says that if I have two events, A and B, and I want to find the probability of A union B, which is basically an OR statement, this or that occurs, I add the two probabilities. But if they overlap, I have to subtract off the intersection, because I counted that twice by adding them. So this is the addition rule for non-mutually exclusive events. And then if they are mutually exclusive, I could get rid of this part. The intersection would be 0. So that's just probability event A occurs plus the probability event B occurs. Now, an example for that is I draw a card from a standard deck of 52, say, what's probably getting a queen or a spade? Well, a queen or a spade. Now, there is a queen of spades, so it can be both. So you can't just do the probability of getting a queen, 4 out of 52, plus the probability of getting a spade, which is 13 out of 52. It wouldn't be that because you counted that queen of spades twice in there. So this would be an example of a non-mutually exclusive event where you use this formula. However, if they are mutually exclusive, you can use the probability of a king or a queen. A king can't be a queen. So these can be calculated as 4 out of 52 plus 4 out of 52. Now that's the addition rule, a little review of that. And the multiplication rule, which we're doing today, is this one right here, which you just derived. And the probability with independent events, which we've done before, you just have to multiply the two. Now let me say this, is if I draw two cards, what's probably getting two aces? If I don't replace them, then drawing the first card affects the probability of the second. Now if I did say I'm going to put the card back, the probability of drawing the first ace won't affect the probability of drawing the second ace because I put it back and I reshuffled. Okay, so I'm going to have my bag with 4 white marbles and 3 black. Put these in the bag. And these are the probabilities we're going to calculate. The probability of getting 2 black without replacement. So this probability of getting a black would be 3 out of 7. And the probability of getting the second black, now there's 2 blacks left, and there's a total of 6 in the bag. So this would be my calculation. This is 6 over 42, or I could reduce that to 1/7. Okay, now let's do the 2 blacks again, and we'll say with replacement. So I'm going to draw the first black, and then I'm going to do it again. So go ahead and calculate that probability. Okay, that probability would be the probability of a black on the first times the probability I get a black on the second. Now in this case, the black on the second doesn't depend on the first one because I put it back in. So these two probabilities don't have to be adjusted. My sample space is still the 7 marbles. So I have 3 out of 7 times 3 out of 7 again, which gives 9 out of 49. Okay, this next one is a little confusing and will throw some people off because I want to see the probability of getting one black and one white without replacement. Now, does it matter if I get the black one on the first draw or the second draw? I don't believe so. The way it's worded, I want one black and one white. It doesn't say which order. So when I do this, I really have to say that this is two probabilities. I'm going to say that's the probability that I get a black on the first and a white on the second, or the probability that I get a white on the first and a black on the second. So we're going to be doing this or. Now these two are mutually exclusive, so I'm going to calculate these separately. The first one I'm going to calculate is the probability that I get a black on the first and then a white on the second. So that's a probability that I get a black on the first times the probability that I get a white on the second, given that I have a black on the first. Now, since this is an or statement, that either of these can happen, plus the probability that I get a white on the first times the probability that I get a black on the second, given that I get a white on the first. Okay, that would be probability to get a black on the first. There's 3 black. There's 7 marbles. Probability to get a white on the second. There's 4 white still in the bag. Given I took a black out, there's a total of 6 marbles in the bag. Plus, probability to get a white on the first. There's 4 white. There's 7 marbles. The probability to get a black on the second. There are 3 black and there are 6 marbles left in the bag. This is 12 out of 42. This is also 12 out of 42. That's 24 out of 42. And that reduces to 4 out of 7.